Now I also want to talk a little bit about a two-dimensional rotational inertia. So for example, if we were to consider a rotational inertia of a disk, how will that change from the rotational inertia of, say, a rod that we had before? Well, the formula for moment of inertia is not going to change. It's going to be exactly the same. I equals integration r squared dm. But this dm is going to change for this case. So for a disk, for example, if you have a disk, what is going to be your dm? Well, your dm, if the disk is rotating about its central axis, your dm is going to be this area, right? We can consider this dm. This is going to be our dm, which is going to have a thickness, let's say dx, right? But it's also going to be a thickness, and it has an area that it has to go around. So in this case, instead of talking about the linear density, we are going to talk about the surface density, right? So in this case, the surface density is going to be sigma, right? Sigma is equals to dm over dA instead of over the dl or dx as we had before. And sigma total will be total mass of the object divided by the total area of whatever object we are looking at, right? Now in this case, the dA is going to be slightly different. So dA, for our purposes, is going to be dm over r dz or r dr, whatever you want to call it, and d phi, d theta. So it's going to be this r that I've noticed, right? So it's going to be dr on the thickness. R is going to be how far away it is from the center, and dm is going to be the mass of this object, right? And the fact that you have to go all the way around in a circle, that's going to give you your theta. Okay? So your sigma is going to be dm over r dr d theta. This means sigma can also be written as m over a, m over the total area, r dr d phi, d theta, in this case, is equals to dm. Okay? Now, how do I find what the moment of inertia is going to be? So, in this case, it is going to be I equals r squared, and I'm going to plug this value of dm into here, so it will be m over a r dr d theta equal, that's it, right? So it will be m over a r dr d theta. Good. Now in this case, we cannot just integrate over one variable because we are now going to have two variables. So these integrations are going to be over double the integration, double integrals, right? Which means one of them is going to be over dr and the other one is going to be over d phi. So let's rearrange it and then try to figure out where the limits of integrations are going to be. So m over a is a constant, which can easily be taken out. The first integration will be r cubed, so I'm combining these two, dr. Note d phi is independent of r, so I can just simply do d theta here, right? The limits of integration of d theta, so if I was to start from this point and I were to walk all the way across and come back to the same point, this will be from 0 to 2 pi. What about for r? If capital R is my big radius, then the limits of integration will be from 0 to capital R. Correct? Good. Once we have this, we can solve these and come up with an answer. So this is going to be m over a, r4 over 4, limits of integration from 0 to r, and this is going to be theta from 0 to 2 pi, right? This implies my answer is going to be m over a, and you can put in a bracket if it makes you feel better, r4 over 4 minus 0 over 4, so I'm just not going to write it, dot 2 pi. Right? So I plugged in this value in here and that value in there, and then that's going to be the solution. Good. This is what our solution looks like. However, this is not the same units as that. So we have to go back to those units. So this implies this 4 will get canceled with this 4. And I'm going to rewrite this as mass. What's an area of a disk? Pi r squared. Is that it? That's about it. And if the r is a capital R, the total area will be capital R divided by this. So it'll be R4 divided by 2 times pi. So pi will get canceled, r squared will get canceled here, and I'm going to get 1 over 2 mr squared, right? So now I have an r squared and an m and a unit 1/2, which is associated with it. That will give me the moment of inertia of a disk rotating about its center.